Hello and welcome back. My name is Brianda Hernandez Rosales, and in this part 2 of the 6-part series looking at the feasibility of rainwater harvesting in arid environments, we will be taking a look at the rainwater harvesting equation. Here is a quick outline of the remaining videos. Part 1 was a quick introduction to the project. Part 2 will be looking at the rainwater harvesting equation to determine the volume that can be captured. Part 3 will look at the aquacrop model. Part 4 will take a look at the area that can be cultivated solely using the harvested rain. Part 5 will be looking at the cost and maintenance it takes to install a rainwater harvesting system. And in Part 6, I will be doing a run-through example based out of northwestern Arizona on the Hualapai Reservation. So, to get into it, the rainwater harvesting equation, as listed here, is a volume that can be collected, which is determined by the rainfall depth multiplied by the area of the catchment that will be collecting this rainwater, and then also multiplied by the runoff coefficient, which is determined by the material of the catchment. The rainfall depth is just the amount of rainfall that falls in the area. You can get this information if you have reliable rain gauge or local historical data for your area. You can also get rainfall information and data sets from Prism Climate Group's website, which I will be demonstrating in a bit. You want to make sure that you have at least 20 to 30 years of precipitation data. This will allow you to really encompass the wet years, the normal years, and the dry years. And working with monthly precipitation data will work just fine, as daily data might be too complex to work with, and yearly data might not encompass the individuality of the months. You want to make sure that you use a water year for your data set. So this means that you would start the beginning of a water year in October 1st in order to encompass the entire winter season, and then end on September 30th, which would also encompass the entire summer season. So I will be doing a quick run through of Prism Climate Group's website so you can understand where you can download some precipitation data. So here, as you can see, Prism Climate Group gathers different climatic observations from different monitoring networks and then applies this very sophisticated measures that ensure quality control, which then develops different spatial climatic data sets for different areas in the US. If you would like to learn more about the way that Prism Climate Groups develops these data sets, you have some resources here in their main homepage. However, if you scroll down, what I suggest to use is to get the Data Explorer. This would allow you to explore different data sets along the United States. So once on this area, you'll be able to collect a time series for different parameters. So you can look at precipitation, different temperatures, both all three minimum, mean, and maximum, as well as vapor pressure deficit. And here you can actually indicate which state and county you're trying to get information for, or you can put in the coordinates if you have that information. So since I did my research based out of the Hualapai Reservation in Arizona, I will be using that as an example. So the state, Arizona, the county, Mojave. Usually the way it shows it to you is like you kind of have to search, or you can put in, again, the latitude and longitude to be more precise. Here I have it on the town of Peach Springs, Arizona, where my research was based on. And here you can decide what types of precipitation data sets you would like. You can do 30-year normals. You can also get data sets that show the annual values for precipitation and temperature, or monthly values, which is what we're interested in, as well as daily values. 30-year normals will also work. In this one, you can do resolutions of 4 kilometers or 800 meters. which is a little bit more precise. For the monthly values, again, you can start your month anywhere, but as suggested, definitely start in October. So if we look at 30 years of data, so we start in 91 to 2022. They also have up to the current year. However, that is subject to change. So I would suggest to just stick to the most completed year, which would be 2022 in this case. And again, I'm setting it to the end of the water year of September. You would then also have the option to get the information using a metric system or the English system. So we do English, we'd retrieve that time series. You will get the precipitation and temperature patterns for the last 30 years or the indicated time that you want your data set to be. Once you have retrieved the time series, it is important for you to download the time series, as that is what you're going to use to determine the rainfall depth for your rainwater harvesting feasibility. Once you download the data set, it'll be in a CSV format, and it'll give you information about the time series that you downloaded, the location, what variables you're downloading, the spatial resolution, the period, and then you'll have the date column, which has the year and the month, as well as the precipitation in inches, and then the temperature in degrees. Because you are downloading a large amount of values for different precipitation years, one of the things that I did for my research was classifying each year as a dry, normal, or wet year by using the Indian Meteorological Department's classification, which says that a dry year is less than 20% of the long-term average. A normal year is plus or minus 20% of a long-term average, and a wet year is greater than 20% of the long-term average. So for my data set, if my long-term average is 245 millimeters a year, then a dry year will be 20% less of that. A normal year will be plus or minus a 20% from 245 millimeters. And then a wet year will be 20% greater than the long-term average. When the data is put into a probability density, you can see how these dry, normal, and wet classified years fall into place. This is important because you will end up with 3 different numbers instead of just one, making the precision a little bit closer, especially during this time where climate seems to be a little erratic and have no established pattern. So how do you classify your data set into a normal, wet, and dry precipitation year? I will be showing you how to do that quickly. When you download your data, you can see that your date is in the format of your year and then your month, and you want to make sure that you add another column just indicated for your month. So we'll be inserting a new column. We'll actually be inserting another column for the water year. So name this water year, and then your month. And for your month, you're going to highlight everything and separate this data. So we'll hit the data tab, hit text to column. If you click on the delimited, what this is going to do is going to look at the individual data and then separate it based on what you tell the Excel to separate it in. So we're going to hit other and then put that that the data that you want separated is being separated by a dash. Hit next. This will then separate the data. Hit finish, and you get your year on one column and then your month separated on a separate column. As for your water year, you'll be doing just a quick formula. So you can start with 1992. For your very first 3 months, you want to make sure that you add a year to the date. So drag that down for the first two or first three, and then here, two. And then you're going to drag that down all the way again until September, and then repeat the formula that you did for October 1991. Again, drag it for the first 3 months, and then just indicate that you want this year for the rest. Okay, and now that you have about two sets of formula indicating what you want to happen, you're going to go ahead and highlight it, and then go ahead and click on this. And you just want to make sure that this was indeed correct. And as you can, and yes, you can see that my water year starts in October and goes all the way on until September. Again, same thing. So that's a quick and easy way to add your water year. Once you've done this, you're going to put this into a pivot table. You're going to click your year, water year, and your precipitation. And your sum is just how much water fell in the area for the water year of 1992. So that was about 9.6 inches. And this is where you want to start characterizing or determining what the 20% plus or minus of your normal or long-term average is going to be. So another quick formula, looking at the average for your sum of each year. So your long-term average is going to be 8.989 for from 92 to 2022. So your dry year is going to be 20% less than the long-term average. So we'll do a quick formula, which is just this number, and it's going to be minus that 20%. So for a dry year, anything that is 7.9 or below, 7.19 or below will be considered a dry year. And for a wet year, anything that's equal to or above 10.78 will be considered a wet year. And so a normal year will be any of the values that sit between them. So we'll just put this as a long-term average. Okay. Once you have this information, you can now separate these to determine a normal wet and dry precipitation year. And a fast way to do this, all this is going to get a little bit more complex because more information is needed. We're going to copy this, create a new tab, and turn this into a table. This just makes it easiest to work with. Go ahead and click OK. So now that you have this information, and let's grab this. So we're going to insert a new column. Name this characteristic. So we can click on the precipitation, and this will have it in ascending order. So if it's 7.19, we're going to deselect everything and only select the ones that fall in the dry year. Hit OK. So then we have 7 different or 8 different years that are within that data set that are considered dry. Okay. And we'll do that. We'll do the same thing for every classified year. So now you have it for each year in your data set, what is considered a normal wet and dry precipitation year. However, you still want to do that for each individual month, since you'll be looking at monthly averages and how much water you can collect per month if you decide to do a rainwater harvesting system. So we'll hit back here. And again, you do have your months here. The best way to do this is you're going to create another table. Okay. We're going to add a characteristic. Okay. And with this information here, again, okay, and let's just make sure that here, this should be water year. So we can look at what a dry year would be. So we know that these years are considered a dry. This will allow us to just kind of get that data so we're not moving back and forth between different years or different tabs. So, paste, normal, and cut. Okay, so now that your data set is in a table, you'll be able to, again, select the water years that fall within these categorized precipitation years. So we'll start with dry. So for dry, you'll just select all of the years that were considered a dry year. So consider this a dry year. I find it easier to do the dry and the normal years first, and then in order to label the normal, you can then go to characteristics and hit the blanks, and then you know that this is the normal. Okay, and so now if you select all of your months now have the same labeled characteristic of a normal, wet, and dry year for each year. And this is going to come in handy when you decide to put this information in the aquacrop model, because that's where you'll be able to get the different volumes of water for each year. So you want to get the averages for each month. So one last thing, I'm gonna create another pivot table. So we can call this one pivot 2. So here you'll be able to, so now you'll be creating a new pivot table to just get the averages for each month, depending on which characteristic it is. So this will be a filter. Precipitation, you can do, and we're going to do all averages since we're averaging everything out. Okay, so we can look at a dry year. And for a dry year, here are your average precipitations for all of your different dry years that you listed. So all 8 years that were dry, the average monthly precipitation and monthly minimum temperature and maximum temperature will be listed here. And I suggest to separate these out and put them on a separate, copy the cells and put it on a separate sheet, just because it'll be easier to work with when you work with the pivot table, as a lot of you may know, just kind of changes constantly. Dry year. And so we don't get confused. So that's for my dry. Again, filter it out to a normal year. This will be my normal year. Okay, so this is your ready to go data. So I would put that down. Okay, and this is the information that you'll be using to put into the aquacrop model. Again, this is if you want 3 separate values for what you would classify as a dry year for your area, a normal year, and a wet year. The next part of the rainwater harvesting equation is to determine the area of the catchment. So if you will be using a roof, you would want to make sure that you know the area of the roof, because this will determine how much water can be collected. So if you have a roof that's 1,000 square feet compared to a roof that's 2,500 square feet, you're definitely going to get more water on a 225 square feet roof than if you would a 1,000 square feet roof. Getting this information is very simple. You can do a rough measurement of your roof, or if you have that information available to you, then use that. The last part of the rainwater harvesting equation is the runoff coefficient. And the runoff coefficient is just based on the material of the catchment area. This shows the imperviousness of the material and infiltration capacity. As you can see on the right-hand side, you do have some runoff coefficient percentages. So if you have a galvanized iron sheet metal roof, then 90% of the water that falls onto that catchment will run off and is available for you to capture. If you have a sheet roof, it's 80% of the water that hits that catchment will run off. And the reason for this is because as you change the material and the type of roof, you change the imperviousness and infiltration capacity. So for instance, a tiled roof will absorb about 25% of the water that is falling onto the roof, and only 75% of it will run off. If you have, let's say, a wood roof, the runoff coefficient for that would be even less, as wood tends to absorb a lot of the water. The runoff coefficient also takes into consideration the water that cannot be collected due to spillage or fast evaporation. Now to go over a quick example for the potential volume of water that can be collected during the month of August in northwestern Arizona on the Hualapai Reservation. As you can see, my rainfall depth was calculated using normals for August from 1991 to 2020. This is classified as a normal precipitation year, meaning that if I were doing the values for a wet year, I would have potentially more volume that could be collected, and during a dry year, I would have less. So my rainfall depth is 0.1183 feet or 1.18 inches. You want to make sure that your units are consistent. As for the area of the building that was being considered for harvesting water is 2,290 square feet. And the material was galvanized metal, meaning that the runoff coefficient is 0.9, or that 90% of the water that hits the metal roof will run off. When you multiply all those together, again, make sure your units are consistent. You will end up with 243.8 cubic feet, which then when you multiply it by 7.5 gallons, which is a cubic foot, you get about 1,842 gallons that you can collect during the month of August during a normal precipitation year on the Hualapai Reservation. That is an incredible amount of volume just for a single month. That concluded the rainwater harvesting equation. The next part, we'll look at the aquacrop model to determine how much water is needed to cultivate a certain plant. Part 4, we'll look at the area that can be cultivated using that information from the aquacrop model. And then part 5, we'll look at the cost and maintenance, and part 6, a run-through example. Again, if you have any questions about this project, please feel free to contact me at briandahernandez90@outlook.com or Dr. McCarthy and or Dr. Lutz at their respective emails. Thanks.